Hi everyone and welcome back. Today we're going to talk about circuits. So let's get started first with the idea of circuits in practice. So why do we care about circuits? This is one of the first things that I ever did when looking into circuits back in high school. This was the very thing that actually got me interested in physics. And that was creating a circuit with a battery and a light bulb. So you can see here in practice, we have a light bulb connected by two wires, one going to a battery, and that's just like a AA battery that we use in like remotes and stuff. And this is a switch, or um, basically, if you connect these two, you can complete the circuit or turn off the circuit. So that's why they call it a switch, like a light switch, turning something on or off. Okay, so if we were to connect these two, then we would complete this circuit and the light bulb would produce light. And this is a schematic. Let me quickly change colors here. This is a schematic of that exact thing. So we've got our battery over here and the wire to a switch and to a light bulb. Okay, so we'll see these types of schematics over and over again throughout this lecture, and it will represent what we're looking at physically. Okay, so a lot of times, or actually all the times, all the time, in um, in creating these circuit diagrams, we will have a battery and probably a resistor. So there's certain um, symbols that will represent each of these. So this is a battery, this longer side being the positive side and the shorter side being the negative side. Okay, so this is what represents a battery. This is what represents a switch, and we won't really talk about that much. I just wanted to show you guys an example of that. And then a light bulb. So that's a light bulb. If we want to go ahead and put resistors on here, a resistor is like a little squiggly shape, like that. And it would kind of go along here. So this would be a resistor. Whoops. Resistor. Nope. Wow, I spelled that so wrong. Give me a second here. All right. Resistor. There we go. Um, so we have resistors, batteries, and light bulb switch. And then as other things come up, I will talk about those as well. So let's go ahead and start looking at different types of circuits. There are two types of circuits. There are circuits in parallel and circuits in series. And then, of course, when we start combining those, and we'll see that here in a minute. So let's talk about resistors in series. Okay, remember that a resistor limits the flow of charge in a circuit. Okay, so it's slowing down our flow of charge or our current. Okay, and then when that flow of charge or that current um, um, I'm sorry, this is in series when the flow of charge must flow through devices sequentially, so one right after another. A very popular example of this is Christmas lights or holiday lights. Um, these typically will be, or actually all the time, are in series, and that's why when you have a string of lights and one of the light bulbs go out, all of them will go out. Okay, they'll have like certain sections of this, but say if this one goes out and stops working, then this whole thing will stop working because that flow of charge is no longer going through that light bulb and continuing here. Okay. Um, and here is a another image of this, or a schematic. where we've got some voltage being applied or a battery. So this is a battery. Again, we have that positive side, and then this would be the negative. Okay, and we have resistors. Okay, so there's 3 resistors in this diagram here. This is your flow of current. So it's going from the positive to the negative of the battery here. And with that, in series, the total resistance is going to be the addition of each of those resistances. Okay, so this is the total resistance in series. That's very important, okay? Because in series and in parallel, they are going to be calculated differently, okay? So if I take each of these resistors and find their resistance, or it's given to me, adding all of them up will give me the total resistance of this series of resistors here. Okay, so it's simply just adding them up. So this is the same as this. So this diagram 1 is the same as this diagram 2. Okay. Again, we have our voltage with the positive and negative. We have our current flowing through, and this is our total resistance in series. Okay. So I have here our formula that we can use, or we can say it's like the summation of all of the resistances. This isn't super important, but this is what we're looking at here, okay? We won't be looking at a ton of resistors, probably max 3 in a row, okay? All right, so let's go ahead and look at an example of this. So suppose we have the voltage output of a battery in the last figure that we were just looking at, and it is, whoops, stop, 12 volts, okay? This is my voltage. And the resistances are R1 is equal to 1 ohm, R2 is equal to 6 ohm, and R3 is equal to 13 ohm. What is the total resistance? So remember what I said, that our total resistance, R in series, is going to be the addition or the sum of all of our resistances in series. So this will be R1 plus R2 plus R3. Okay, so that would be 1 ohm plus 6 ohm plus 13 ohm. Excuse me. So 1 plus 6 is 7 plus 13, that will give us 20 ohms. So this is my total resistance. Okay, again, we are looking at the diagram we just saw. Okay, this one here. Maybe I should redraw it. So we would have this, this. Bear with me. My resistors are not perfect. So we have R1, R2, and R3, and our voltage. Okay. Usually I would draw it a little nicer than that, but it is what it is for now. Okay. Now we want to find the current. So this is going to be the overall current of our system here. So our current, we're going to say, is in this direction, since that's what it said in the diagram, or has in the diagram. So remember that voltage is equal to I times R, our resistance. Okay, so current is I. So we can go ahead and solve for I is equal to R. Nope. Sorry, getting ahead of myself. V divided by R. Okay, so then we plug in our volts. We have 12 volts divided by 20 ohms. Let me see what that would be. Okay, so my current is 0.60, and I know that current is in amperes, so A. I hope you can see that. I should be writing in a white pen. Let me erase that and put it in white, just because I think it's a little easier to read on this darker background. So again, voltage, 12.0 volts, divided by our resistance that we just found, 0.60 amperes. Okay. All right, so those are the first two parts, pretty simple, straightforward. Now we want to find the voltage drop in each resistor and show that these add to equal the voltage output of the source. So this is implying that our voltage drop in each resistor, V1, V2, and V3, would be the total voltage overall, okay, or that 12 volts. This is what this is trying to imply. So let's check if that's correct. So we would do, let's see, we have our resistance, we have our current. Our current will be the same throughout the entire system here, our entire circuit. Okay, so note that current remains the same throughout series circuit. Okay, so with that information, we can start finding each of the voltages. Okay, so let's go with V1. So that would be V1 here. Okay, so the voltage across this guy. And I'll talk a little bit later about how we would physically find these values in practice in like a laboratory setting. Okay, so here is V1. We know that's equal to I, which is the same throughout, and times its resistance of that first resistor. Okay, so we have I, which we just found was 0.60 amps. And our resistance was given to us as 1 ohm. So that's just going to be 0.6 volts. So that's our first one. Then we have V2 and V3. So IR2 and IR3. Again, our amperage or our current stays the same. And then we have R2, which was given to us as 6 ohms. Okay, so let's take that times 6, and we get 3.60 volts. And then our third one here, same amperage, and our resistance is 13 ohms. So 0.6 times 13, and we get 7.8 volts. Okay, now let's put this to the test. Let's say V is equal to, and we're going to add all of these up, so 0.60 volts plus 3.60 volts plus 7.80 volts. So our total voltage is exactly 12 volts. So it checks out. So this shows us a few different things. So we found, or we're basically told that the overall current stays the same throughout the series circuit. Okay, so this doesn't change anything. Our current remains the same throughout each resistor. Okay, but our voltage drop across each will be different. So V1, V2, and V3 will all have different values, but adding all of them up, or the sum of them, will equal our overall voltage. Okay. All right, let's move on to part D. This asks to calculate the power dissipated by each resistor. So we can use a couple of different things. We can, if you remember from the last lecture, power can be calculated with in a few different ways. So we can use this here, P equals IV, or we can use P is equal to I squared times R, whichever way you want to do it. I think what I will do, this one probably be easier, but this one has the resistance that was given to us, so I'm just going to go with that. But you can calculate it in either way. It should give you the exact same value. Okay. All right. So let's go ahead to the next page and start on that. So P is equal to I squared R. Okay. And remember our resistances. I'll go ahead and write those down. 1.0 ohms. R2 is equal to 6 ohms, and R3, I believe, was 13 ohms. And our current we found to be 0.60 amps, right? Perfect. Okay, so we are trying to find the power dissipated at each resistor. So we will have 3 different values. So let's do the first one. The power dissipated at the first resistor. So that's going to be I squared times R1. Okay, so it'll be 0.60 amps squared times 1.0 ohms. So I'll just do 0.6 times 0.6 times 1, of course, is going to be 0.36, and power is in watts. Okay, so this is the first power that was dissipated at the first resistor. Okay, power dissipated, if I'm spelling that right, at R1. Dissipated. I spelled it wrong. Surprise, surprise. Okay. Okay. So we'll need to do that for each of our resistors. Okay. All right. So P2 will then be 0.60 amps because that remains the same, and then multiplied by 6 ohms. So 0.6 times 0.6 times 6, and we get 2.16 watts. P3 13 ohms, and we get 4.68 watts. Okay, so these are the power dissipated at each resistor. Okay. Whoop. All right. So moving on, to part E. Find the power output of the source and show that it equals the total power dissipated by the resistors. Okay, so this can be found using our overall voltage that was given to us, 12 volts, and our current that we found. So this would be P is equal to I times V. So our current, 0.60 amps, times our overall voltage, which was 12 volts. Okay, so 0.6 times 12, and we get 7.2 watts. And we're trying to show that this power is equal to the sum of each of these. Okay, again, let's look at the wording. Find the power output of the source, which is what we just found, and show that it equals the total power dissipated by the resistors. So this is asking for the sum. Okay, so let's go ahead and do that. So P is also going to be equal to P1 plus P2 plus P3. Okay, so I'm going to go ahead and do that in my calculator. So 0.36 plus 2.16 plus 4.68, and we get 7.2 watts, which is exactly what we expected. Okay. All right. I know that this stuff is a little new, so if you take your time through this, it'll probably make more sense. Okay. All right, so let's remember some major features of resistors in series. Okay. The resistances add together. This is a major part of this. So in series, we can add the resistors together. Okay, and that would be our total resistance. So this is our total resistance. Okay. The same current flows through each resistor in series. We saw that. And individual resistors in series do not get the total source voltage, but divide it. So it's not that it divides equally, but each resistor will get a portion of that overall voltage. So I should write that down. Each gets a portion of the source voltage. Okay, so it's not that it divides equally, it just gets portioned up. Okay, so V would be equal to V1 plus V2 plus V3 plus ... Okay, very similar to its resistance. All right, so this is where I'm going to pause, and then we'll get started in the next video talking about resistors in parallel.